Hello, I welcome you all. The problem reads the uniform dresser has a weight of 90 pounds and rests on a tile floor for which the coefficient of friction mu s is equal to 0.25. If the man pushes on it in the horizontal direction where theta is equal to 0 degrees, determine the smallest magnitude of force F needed to move the dresser. Also, if the man has a weight of 150 pounds, determine the smallest coefficient of static friction between his shoes and the floor so that he does not slip. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have been asked to determine the smallest magnitude of force F, okay, when theta is equal to 0, so horizontal is in the horizontal direction, and we are also being asked to determine the smallest coefficient of static friction between the shoes and the floor. Alright, so this is a continuation. Part 2 is a continuation where we are determining the coefficient, the smallest coefficient of static friction. So let's start with the smallest magnitude of force F needed to move the dresser. So we need to draw the free body diagram. So there we go. We have the dresser like so. Okay. And then the force we are being told is supposed to be horizontal. F theta is equal to 0 degrees. All right, we've not been given any dimensions of this dresser, and we have the weight acting through the centroid, and we know the centroid will be half span. I mean half span of this dresser. So if it is of length L, then this you expect L over 2 and L over 2. And this weight you've been told is 90 pounds, right? What else? So then we've been told there is friction on the tile floor, and the coefficient of static friction is 0.25. So we expect, let's say the friction force is going to be somewhere there, which is F. Let me call this point here as my point A. Let me call this at FA. All right. And also let me call this reaction from the floor as NA. Okay. And then there's going to be some distance from the edge of the dresser. I'm going to call X. All right. To prevent toppling over, there's going to be this distance X. Of course, we've not been asked to find that. All right. I'm just indicating all the other nitty gritties. So with all this information, how many unknowns do we have? We have 1, 2, 3, 4. Right. So with such a case like this one, and we are being asked to determine the smallest magnitude of F, and we have more unknowns than the available equations of equilibrium, and we are also being asked to determine the smallest magnitude of force needed to move the dresser. So we need to find the force F, okay, that will move the dresser. So we just want to find the force at the very edge, okay, at the very edge. And that force, we will only find this force if we use one of, or we invoke one of the friction equation, where we'll say Fa should be less or equal to mu A Na. Okay, therefore we can borrow this equation and just equate it to this condition, mu A Na, and this is equal to, what is our mu A? We've been told is 0.25 by Na. Okay, so our mu Fa therefore is equal to 0.25 Na. All right. So this is the condition at which the dresser is at the point, or it is impending to move, or impending motion, right? It's almost about to move. All right. Okay. So this is the condition that we are going to invoke for us to determine the minimum force F. We need this condition. Right. So with this condition, then we can go ahead and apply the equations of equilibrium. Let's start with the summation of forces in the y direction. Summation of forces in the y equal to 0. All right, there we go. What do we have? We have minus 90 plus Na. What else? That's all equal to 0. Therefore, our Na is equal to 90 pounds. Right? Then summation of forces in the x direction. What do we have? We have F, okay, minus Fa, okay, equal to 0. And we know what Fa is, and therefore our F will be equal to Fa, which is equal to 0.25 Na. Therefore, our F is equal to 0.25 times Na, which is equal to 90. Therefore, we have a value of 0.25 by 90 gives us a 22.5. So 22.5 pounds. Okay, so 22.5 pounds. Right. So this is the minimum force, or the smallest force, that is needed to move the dresser. This is the force at the very edge. Okay, at the very edge. Okay, and if we just went a little bit above this, then we expect the dresser to start moving. Okay, right, I guess we are done with one problem. Then we have another problem, which is a continuation. If the man, so let me finalize this. So we say F minimum, or F smallest as it is called, F smallest is going to be equal to 22.5 pounds. All right. Okay. So here we are. Let's now move to the second part, which is to determine the smallest coefficient. So I had to just get a part of this person. So we have F that we have already calculated, F pushing on the dresser. So we expect a reaction force there of F, which we've already calculated as a 22.5. Then we have, let's say we have a force here. Let's say this is our center of gravity for this person. We've been told he weighs, let's say it's passing through there. We've told he weighs 150 pounds, right? And then at this foot here, the front one, since he's pushing, like this force is pushing on him, so we expect the let me call this point here as B. All right, so I'm going to have a force like so that will oppose that particular force, and then I have a normal force NB. I'm just giving them as NB, and then I have a distance from the center of gravity. I'm going to call Let me call it D. All right, but we are not going to find it. All right. So with this information, um, we need to find we need to find okay, let me write this one the other side. I prefer writing it the other side. Nothing changes. I just prefer writing it the other side like this. All right. Okay, sorry. I write it the other side like so. And this is our FB. Okay, this point is B. All right, then I will have the resultant. Let me say the resultant is somewhere here. Okay, this is my resultant, R. And then I have this angle here, this angle here, this angle here in red that I'm going to call phi. All right, so let's go ahead. So we have summation of forces in the y equal to 0. Okay, there we go. So what do we have? We have minus 150 plus NB equal to 0. Therefore, NB is going to be equal to 150 pounds. Okay, and then we have summation of forces in the x direction like so. Let me draw a boundary here. All right, summation of forces in the x, we have FB, okay, minus 22.5 equal to 0. Therefore, our FB is going to be equal to 22.5 pounds. All right, so now we want to find the smallest coefficient of static friction between the shoes and the floor. Okay, so of course this is one of the methods. So we know that mu, I'll call it mu B, okay, is equal to tan phi, which is equal to FB divided by NB. This is equal to, what is our FB? Our FB is a 22.5 and then our NB is 150. Therefore, our mu B, static coefficient of friction, is equal to what is 22.5 divided by 150. So we get a 0.15. Therefore, our mu B smallest, okay, our mu B smallest is therefore equal to 0.15. So this is the smallest coefficient of static friction between his shoes and the floor that he should not slip. Right, so we found the smallest static coefficient of friction, and we've also found the smallest magnitude of force, smallest magnitude of force needed to move the dresser. I guess we are done. And I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and see you in my next screencast.